Host, welcome to another episode of Above and Beyond Aviation. As we find ourselves standing at the brink of another exciting adventure into the limitless expanse of sky, we take a moment to reflect on the marvel that is aviation. Once a dream of mankind, now a reality, aviation has opened doors to unexplored horizons and broken down barriers of distance and time. Today, in our quest for knowledge, we have journeyed beyond horizon, stretching upwards above the clouds. Here, amidst the serenity, the science of flight takes on a mystical aura. Our aim, to unravel the intricate mysteries of airborne physics, a science that has captivated the brightest of minds for centuries. Our journey begins with delving into the power of lift. This invisible force, often underrated, is the magic that defies gravity and enables an aircraft to soar high. It's a concept that baffles and amazes in equal measure, a force that we've harnessed to our advantage. And yet, there remains more to discover. In our endeavor to understand lift, we first explore the impact of different variables. The wings of an aircraft aren't just shaped for aesthetic appeal. They're crafted with precision and purpose. The shape of the wings, their size, and the unique curve, known as airfoil, is designed meticulously to generate lift, counteracting the downward pull of gravity. The angle of attack, that precise angle at which the wings through the air, is a subtle yet potent factor in lift generation. The delicate balance between too steep and too shallow an angle of attack governs the efficiency of lift. And then there's the speed of the aircraft. The velocity at which it moves through the air can enhance or diminish the lift. It is the harmony between speed, the angle of attack, and the wing's design that orchestrates a successful flight. These elements, the wing's size and shape, the angle and the speed of the aircraft, all converge in a symphony to generate lift, a force so essential it is the very essence of flight, the key that unlocks the path to the skies. This exploration of lift is just the beginning. As we continue to delve deeper into the world of airborne physics, we find ourselves fascinated and humbled by the intricacies of flight. We started by exploring lift, the force that counteracts gravity, and learned that the shape and size of the wings, the angle of attack, and the speed of the aircraft all play crucial roles in generating this essential force. Next, we delved into the concept of drag, the resistance an aircraft encounters as it moves through the air. This is a fundamental concept in aerodynamics, a subject that is fraught with complexity and nuance. Drag, in its simplest form, is the opposing force that an aircraft faces as it journeys through the sky. This opposition arises due to the aircraft's movement against the air, a phenomenon that we often take for granted but is fundamentally significant to the science of flight. There is a myriad of factors that contribute to this resistance, but for our discussion, we will focus on two predominant types: parasitic and induced drag. You might wonder about the origins of these peculiar terms. Well, parasitic is a term borrowed from biology, referring to the idea of an entity that depletes resources from its host. In the context of aerodynamics, parasitic drag is the unwelcome guest that saps energy from an aircraft, hindering its forward motion. Parasitic drag itself is further divided into three subcategories: form drag and skin friction. Form drag arises because of the shape of the aircraft. Interference drag results from the intersection of airstreams, and skin friction is due to the air's resistance to the aircraft's surface. Each of these components plays a significant role in contributing to the overall parasitic drag. On the other hand, induced drag is a byproduct of lift, the uplifting force that enables an aircraft to ascend and maintain altitude. Induced drag is most prominent when an aircraft is at lower speeds, specifically during takeoff and landing. Here, the aircraft generates high lift, which in turn leads to increased drag. It's a delicate balance that pilots must master to ensure safe and efficient flights. Now, you may ask, why is understanding and minimizing drag important? The answer is simple: improving aerodynamic efficiency. The more an aircraft can reduce drag, the less power it needs to maintain its speed, leading to fuel efficiency and cost savings. It also contributes to a smoother and more comfortable flight experience for passengers, reducing turbulence and instability. In essence, mastering the understanding of drag is not merely an academic exercise. It is a practical necessity for anyone involved in the design, operation, and navigation of aircraft. The art of minimizing drag is indeed key to improving aerodynamic efficiency. Then, we moved on to thrust, the force that propels an aircraft forward. This powerful force, often underestimated, is the invisible hand that hurls the metal bird into the limitless blue sky. It's a captivating topic that encompasses a world of physics, engineering, and the sheer will to dominate the forces of nature. Thrust is not just a simple push or pull, but a complex interaction of several dynamic quantities. To fully appreciate its vital role in aviation, we delved into the intricate mechanics and design principles behind it. We explored the combustion chambers, the piston engines, and the awe-inspiring jet engines. Each of these different engines has its unique way of transforming mechanical energy into the formidable force we know as thrust. One factor we discovered is the power of the engine. It's the heart of the aircraft, pumping life into the mechanical beast. The engine's power is a crucial determinant of the amount of thrust a plane can generate. The more powerful the engine, the greater the thrust, allowing aircraft to soar higher and faster. Air density, on the other hand, is a more subtle factor. It's the invisible matrix of molecules in which the aircraft operates. High air density means more molecules for the engines to push against, increasing the thrust. Conversely, in areas of low air density, the engines have fewer molecules to interact with, reducing the thrust. It's a delicate balance that requires precise calculations and careful adjustments to maintain optimal performance. Aircraft speed is another significant factor. The faster an aircraft moves, the more air it encounters per second. This increased interaction with air molecules means more opportunities for the engine to generate thrust. However, speed also means increased air resistance or drag, which the engine must overcome. It's a constant battle between speed and drag, with thrust as the crucial mediator. Despite the complexity and challenges, humanity has harnessed the power of thrust to conquer the skies. It's a testament to our relentless pursuit of progress and our unwavering belief in innovation. Understanding thrust and its intricacies not only fascinates us, but also encourages us to appreciate the ingenuity behind every successful flight. We found that factors such as engine power, air density, and aircraft speed can all influence the amount of thrust produced. Finally, we discussed gravity, the ever-present force that tries to pull aircraft back down to Earth. An unseen yet powerful force, gravity is integral to the very fabric of our existence. It is a relentless and omnipresent force that pervades every aspect of our lives, and yet it is so commonplace that we often overlook its significance. It is everywhere and nowhere all at once. It pulls things together, keeps us grounded, literally and metaphorically. In the world of aviation, the concept of gravity takes on an even deeper meaning. It's a force pilots grapple with at every stage of flight. From the moment the wheels of an airplane leave the tarmac to the point they touch down again, gravity is a persistent factor. It is an adversary, a challenge, a constant reminder of the Earth's unyielding pull. Gravity, though invisible, is a powerful actor upon every object on Earth. It pulls everything towards the center of our planet, a ceaseless tug that tries to keep everything grounded. The moment an object tries to raise off the ground, gravity tries to pull it back down. It is relentless and indiscriminate, acting upon everything with equal force. In the vast open skies, aircraft are constantly fighting against this force. Each aircraft, whether it is a small private plane or a massive commercial airliner, is battling this pull. The higher they climb, the more they must fight against gravity's pull. It is a ceaseless struggle, a dance between the earth and the sky. Yet, as formidable as gravity seems, it's not unconquerable. Thanks to the principles of airborne physics, pilots have tools at their disposal to counteract this ever-present pull. They leverage the dynamics of lift, thrust, and drag to keep their aircraft aloft. With every rotation of their engines, they defy gravity, launching their aircraft into the skies and maintaining their flight path. The principles of airborne physics offer a range of possibilities. They allow for the calculated defiance of gravity, enabling pilots to not only counteract this force, but master it. Through careful maneuvering, precise calculations, and a deep understanding of how these forces interact, pilots can navigate the skies with grace and skill. These principles don't just allow pilots to keep their aircraft aloft. They make flight possible in the first place. They allow for the exploration of our world from a bird's eye view, for the connection between distant lands, for the realization of mankind's age-old dream to fly. Yet, thanks to the principles of airborne physics, pilots can overcome gravity's pull and keep their aircraft aloft. Above and Beyond Aviation offers a fascinating journey into the science behind flight, providing insight into the principles and forces that make aviation possible. Explore how these theories transformed over the centuries to mold our understanding of aeronautics. From the simple principle of buoyancy, which guided the Montgolfier brothers to construct the first hot air balloon in 1783, to the complex Bernoulli's principle and Newton's laws of motion, which have been the cornerstone of modern aviation. Our journey through the history of flight will take you from the first kite-like gliders of the 9th century to the mighty jet engines of the 21st century. Be it the Wright brothers' ingenious flight controls, which led to the first powered flight, or Igor Sikorsky's persistent efforts to develop a fully functioning helicopter. We aim to bring their inspirations, trials, and triumphs to life. We delve into the world of aerodynamics, the study of how air flows around objects, to learn about lift and drag, two critical forces in flight. We discuss how wings provide lift, how engines create forward thrust, and how pilots use a plane's controls to steer and stabilize the aircraft. The world of aeronautics is not just limited to science. It is also deeply intertwined with the realms of history, geography, and sociology. We talk about the major aviation milestones, like the first transatlantic flight, the first woman aviator, or the impact of air travel on global connectivity and cultural exchange. We also discuss the future of aviation, where the sky is literally no longer the limit. From commercial space travel to drones, jetpacks to hypersonic flights, we look at what the off-flight might hold. For the innovators, the dreamers, the curious minds who strive to understand how things work above and beyond, aviation is not just an exploration of flight, but a journey that connects the past, present, and future of human invention. And for those still with us, with their head in the clouds and a passion for understanding how things work, our hope is that we have provided a clear, comprehensive, engaging exploration into the world airborne physics. Keep your dreams soaring high and your curiosity alive. Now that we've covered the basics, let's take a deeper dive into airborne physics. The forces of lift, drag, thrust, and gravity are not just abstract concepts, but tangible forces that have a significant impact on every flight. Let's start with lift. Lift is the force that opposes the weight of an airplane and holds the airplane in the air. It is generated by the motion of the airplane through the air and the shape of the wings. For example, when a plane is taking off, the pilot increases the throttle to increase speed. This speed, combined with the angle of the wings, creates a pressure difference above and below the wings, generating lift. Next, drag. Drag is the resistance of the air to the movement of the airplane. It's what you feel when you stick your hand out of a moving car window and feel the wind pushing against it. In aviation, drag is overcome by the force of thrust. Thrust is the force that propels a flying machine in the direction of motion. It's created by engines which push air backwards and cause an equal and opposite force to propel the airplane forward. Think of a rocket launching into space. The force of the exhaust gases shooting downwards provides the thrust needed for the rocket to ascend. Lastly, Gravity. Gravity is the force that pulls everything towards the center of the Earth. It's what keeps us grounded and what an airplane must overcome to fly. An airplane uses the force of lift to overcome gravity and ascend into the sky. These principles of airborne physics have been the bedrock of aviation for centuries, and they will continue to be relevant as we push the boundaries of flight. Whether it's the development of more efficient engines to provide greater thrust, the design of wings to generate more lift, or the construction of lighter materials to reduce the force of gravity, these principles will remain at the heart of innovation. As we continue to innovate and push the boundaries of flight, these principles of airborne physics will remain at the core of aviation. So keep inquiring, keep exploring, and keep dreaming. The sky is not the limit, but just the beginning. We've received some great questions from our viewers about airborne physics, and we're excited to dive into them. One curious viewer asked, "How does the shape of the wings affect lift?" Great question. The shape of the wings, or airfoil, is crucial in generating lift. The curved top surface makes air travel faster over the top than the bottom. This creates a pressure difference, resulting in upward lift. Another viewer wondered, why don't planes fly straight up like rockets? Well, planes rely on air flowing over their wings to generate lift. If a plane were to fly straight up, it wouldn't have enough airflow over the wings, and it wouldn't be able to generate enough lift to stay airborne. And a third viewer queried, what's the relationship between thrust and speed? Simply put, the more thrust an engine produces, the faster the plane can go. Thrust has to overcome drag, and any leftover force is used to increase the speed. Remember, these are just basic explanations, and the actual physics involved is much more complex. But hopefully, this gives you a good starting point. We love your questions and your curiosity. Keep those questions coming. Your curiosity is what drives us to keep exploring and learning. Until next time, remember, the sky is not the limit, it's just the beginning.